is Dr. David Herbst, and he has a long and illustrious history here in the Mono Basin. He was in the first group of young scientists that came to study Mono Lake with Dave Gaines in 1976. And he focused on the alkali fly species at that time, and just expanded into other aquatic insects. And today he's going to talk to us about the influence of drought and flood on aquatic ecosystems. Thanks.
Thank you, Janet. Nice to be here this afternoon with you all. I wish I could have you all out in the field, either at Mono Lake or some nice stream up in the Sierra, but that brings me to think that one of my big gripes about climate science actually is that there's an awful lot of it done from a computer terminal, and there is a real obsession, especially with trying to kind of crystal ball the future, to try and figure out what's coming. And while that is interesting and important information, I am more interested in asking questions about what's happening right now and what have we already observed, rather than guessing at the future. So I want to share with you some information about that touches actually a bit on what Jeff presented. Indeed, I agree with him that the overall trends, the patterns of precipitation and runoff are about the same as they've been for a very long time, but what's really changing is the extremes. And what has already changed is the extremes, and there is a great deal of literature from these climate modelers that have spun out all kinds of different models using a variety of different sorts of assumptions that we are indeed headed for a future of greater climate extremes. But what I want to share with you, at least at the outset here, is to show you that we've already been experiencing those extremes. Okay, so what I want to start with is a graphic that will give you a little bit of an appreciation for what the what changes we've already seen in streams and what kind of changes we're expecting to see develop with even greater intensity. So what you're looking at right here is a typical snowmelt hydrograph for a Sierra Nevada stream, or any kind of a snowmelt stream for that matter. That's what's in blue. And then this kind of radioactively glowing orange line is what we expect to see developing, and has already been developing, with stream flow patterns for an annual period. And one of the things that we are already seeing is a pattern of earlier snowmelt. This has already been demonstrated for a wide variety of western mountain streams especially. In addition to that, because of the earlier snowmelt and the greater proportion of precipitation falling as rain rather than snow, we're also seeing that there's earlier and prolonged low summer flows. And in fact, in many situations, that becomes extreme enough that we see periodic drying of perennial streams. So I can tell you there's nothing like drying a stream out to affect an aquatic organism. That's pretty much a no-brainer. But what we also see is that there are wetter and more erratic winter flows, even rain-on-snow floods occurring. So we see a much more variable hydrograph just during a single year in the record that we've been seeing already, as well as what's projected by the climate models for the future. And of course, we also have warming waters as another consequence of climate warming, both globally and in California as well. Now this is a graphic that maybe some of you have seen before. This is the classic climate change graph. What this is showing is what's known as the warming anomaly, and it's associated with global carbon dioxide increase. So the hockey puck, I mean not the hockey stick, not the puck, change over time, where you see the rapid increase starting in around the 1960s or 70s, rising up global concentrations of carbon dioxide to above 400 right now, is accompanied by a period of consistent warming year after year, starting in 1976, as it turns out, the year that I came here to start studying Mono Lake. I don't think there's any relationship there. In any case, it raises some important questions about what have been the consequences of this pattern that exhibited both globally and locally in California to stream flow. So I asked a simple question related to this particular temperature regime change of hydrographs of Sierra Nevada streams, the flow patterns for Sierra Nevada streams. So given that warming, ask the question, has there been an increase in both the frequency and intensity of extreme events like floods and droughts? So what I did was compare a set of streams from the Sierra Nevada that are unregulated flows that are not associated with streams that have any impoundments above them or dam releases or diversions that would affect the hydrograph, so you know, a pristine type of hydrograph, and compared the period of those flows after 1975 or 1976 with those before that period. So before the warming anomaly compared to after the warming anomaly. And on average, for the 8 unregulated rivers that I could find in the USGS data set, we've got about an average of 40 years before that a warming anomaly, and 40 years after that warming anomaly. So here, for example, is the graphic for the most nearby river that we have these records for. And by the way, there were records for 4 streams on the west slope, 4 on the east slope. This is one of them, the one that's nearest to us. And if you just look at the basic statistics of stream flow, USGS often defines a wet year as being above the 75th percentile of the longest of the long-term average, and that's the blue line, the blue dashed line you see there, and defines dry years as being below the 25th percentile of that long-term average, and that's what you see on this red line here. So the gray arrow at the bottom of this, that's the pre-warming anomaly period, and then the yellow is the post-warming anomaly period. And I basically asked the question, is there a difference in the frequency of occurrence of flood years, wet years, or dry drought years, comparing this period to that period? You can probably all already see that this graphic argues that there's an increase, and indeed there is if you look at the overall statistics then. So if we take all the data from those streams and we look at it on a decadal scale, so 10 years here on the x-axis, and we compare the periods of drought before 1975 to the periods of drought after 1975, they change from occurrence from about every 1 to 2 years to about every 3 to 4 years. Highly significant difference there. And for droughts, from about every 2 years to almost every 3 years. So an increase both in wet, dry years in the frequency of occurrence of potential drought and flood years. And if we look at the intensity of that, it's the same situation. So here we're looking at the intensity of droughts in the period before 1975 and after 1975, and same thing over here with floods. And so what you can see is that here's the 25th percentile demarcating the dry drought years, and you can see that the droughts are deeper. They're more severely depressed than they are in the period before 1975, and the same thing with floods. The floods are more intense, more severe in the post-1975 period here during the warming anomaly. So this just sets up an interesting foundation for trying to understand what the present and recent occurrence of floods and droughts are in Sierra Nevada streams, and how they have already been historically developing. This is not something that's in the future. This is something that's been with us during this warming anomaly period of the last 40 years. So we have a data set that we've collected from a variety of different streams, our Sentinel stream surveys in the Sierra Nevada that run east slope, west slope, north to south from about McCloud River on the north to Sequoia National Park on the south, and we've been following changes over time. I'm just going to show you some of the more recent data that we've worked up that actually runs through the period from 2010 to 2015. This encompasses some important hydrologic variations. In the 2010 actually started off as about an average year, slightly above average actually. 2011 was a huge year, much like the year we're in right now. And then starting in 2012, we had the development of more and more intense drought. So one of the questions about the data set was, are we seeing actual warming temperatures in the streams? And here you can see that that's the case. It actually doesn't look like a whole lot, because these are observations taken from the sample day, consistent sample days across each and every year of the increase. These are still pretty cold streams, but it doesn't show you the range of variation of what we look at if we look at actual thermographs that are in streams, much like the ones that Ellery was describing that she was using, where you get pretty consistent long-term and frequent readouts of temperature. And in that case, we see temperatures that can go above about 20 or even 25 degrees centigrade in many of these streams, especially during these drought years. And that has dire consequences to aquatic life, because once you warm up stream temperatures, not only is there a threat to the physiology of those organisms because of those warming temperatures as a direct effect, but also because oxygen is much less soluble as the water warms. So they're actually undergoing a respiratory stress at the same time as they're undergoing a lethal stress from the effects of temperature itself. So if we look at some of the more consistent records that we have from those temperature probes that we have in the streams over time, one of the interesting things that we see, and this goes to the idea of refugia in streams, is that you would expect that all these streams are consistently warming over time if you look at the period of high flows in 2010 and 11 and then into the drought. And we do see that pattern developing in these bigger streams, Pittman Creek and Deer Creek. But if we look at their tributaries, the smaller streams that flow into these bigger streams, the pattern is actually opposite. The smaller streams, as the drought develop, are actually becoming colder. So insofar as temperature goes as a stressor, it looks like these small streams may be refugia, and that's likely owing to the fact that there's a lot of groundwater that comes into those streams, and groundwater is kind of a refrigerated below ground source of flow. So rather than it just being surface flow that's exposed to those warming air temperatures and is warming, like we see in these bigger streams, the smaller streams with their smaller flows and greater proportion of flow that's coming in from groundwater are actually cooling over that period of time. So even though they're stressed by the low flows, insofar as temperature goes, these small tributary streams, because of the influence of groundwater, may be refugia type of habitat. So that's an important thing to bear in mind insofar as the importance of headwater streams as climate refugia for aquatic invertebrates, which is what I'm going to go on to tell you about. But before I do that, I want to tell you something else about what streams experience as they dry out during drought conditions. So there's two basic types of habitats that we find in streams, riffles and pools. Riffles, so streams, if you've ever been in a stream, they undulate deep to shallow as well as meander side to side. And as they undulate deep to shallow, they're changing from a pool habitat to a shallow riffle habitat. Shallow riffle environments typically are very rocky, turbulent flows, and so there's a lot of oxygen there, a lot of diversity of the kinds of rocky habitat that's on the bottom that the insects inhabit. Whereas pools are these depositional zones that are typically places where there's a lot of sediments that accumulate, and as a consequence of that, a lot of oxygen deficit that can develop because of decomposition that goes on in those pools. So over time, what happens then in the sequence of drying during drought years is that the channels start to contract, so the overall habitat area is being diminished. But what's also going on, as you might imagine from this profile of undulating shallow to deep, is that the shallow portions of the streams is that portion of the stream that's first emerging out of and drying out as a stream channel dries. So the proportion of habitat as the drying goes on is changing from one that's typically dominated by riffles to one that becomes dominated by pools, and even at an extreme becomes a series of isolated pools where flow, if there's any at all, is kind of at the bottom of the profile of those pools and is not very swift at all. And in many cases just stops altogether. So you're changing a flowing water environment to a standing water environment. And of course, at the extreme, the channels dry out altogether, in which case the bugs all die. So what's the consequence of this? One of the things that we see is how there are changes going on in the streams in terms of the resource base of the stream, the algae and the organic matter. Basically, the food web of stream ecosystems is comprised of the algae that grows on the stream bottom, supported by sunlight that allows photosynthesis to go on, and the organic matter that falls into stream channels from the riparian area, from the trees and vegetation that grows alongside streams. And in the fall, when the leaves fall, a lot of them fall into the stream, and they start to decompose. Bacteria and fungi grow on those leaves, and they become a real valuable food resource. But at the same time, there's also a lot of oxygen being taken up. as well as generating oxygen in the case of algae, they also take up oxygen. They have to respire as well. And so at night, when they're not photosynthesizing, an extensive growth of algae in the stream channels can produce a big oxygen deficit, just as the bacteria and fungi metabolizing all the time are removing oxygen from the stream. And so there's a lot of fouling of the stream bottom that goes on by the growth of this algae, the occlusion of habitat space that would otherwise be inhabited by bottom-dwelling organisms, but it's also removing oxygen from these now diminished channel sizes that, that these streams start to look like as the drought proceeds. And so the main players that I've been interested in are the aquatic invertebrates in these streams. There's hundreds of species across the set of sites that we've been studying in the Sierra Nevada. And this is one of them. This is a mayfly called Epeorus. It likes to graze algae off rock surfaces. It's a very sensitive organism, really likes to live in swift water, and again grazes by scraping algae off rock surfaces. This is a stonefly called Pteronarcis. You can see it along the bottom of it. It's got these gills here that look like these little pom-poms, and that's how it gets oxygen out of the water. And it is also one that requires high oxygen environments and lives in these shallow rocky riffles, just as the Epeorus we just saw. This is kind of the tiger of the stream, Doronaria baumannii. It's a big predatory pearlid stonefly. It also has these pom-pom gills along the side, very actively moving amongst rocks in shallow water zones, looking for its prey, which is other aquatic insects. This is a caddisfly. They build a case around themselves that they carry around. Most of them are mobile. Some actually attach themselves to rock. They use silk to build these cases. And here is another mayfly. This is Drunella spinifera. It grows spines along its backside. And those are especially stimulated in the presence of fish because they're anti-predator adaptations for it. But another species that likes to live in riffles. All of these that we're seeing are riffle-dwelling species, including this one, Brachycentrus americanus. It again is a caddisfly, builds a little house, chimney-like case around itself. Also grazes on algae and collects detritus from in between rocks. All riffle-dwelling organisms. So what happens to these critters as the drought develops? I forgot this guy, Cynigmula. So another mayfly, another very sensitive mayfly, also a riffle dweller. So, if we compare, now you saw that we were collecting data from 2010 all the way through 2015. If we compare the severe drought year of 2015 to wet and average flow years, those early flow years, and look at the profile of how organisms change, what you're looking at here is a coefficient of change here. If you see numbers above 0, they're increasing in that drought year. If it's below 0, they're significantly decreasing in that drought year compared to the wet and average years of flow. The green bars are the sensitive EPT species that I just showed you a profile of species for. So what you can see is that there's far more species that are being depleted as a consequence of drought than are increasing. You see there's only one EPT up here that's increasing. And so these tend to be those organisms that are dwelling in pools, that are adapted to life in those deep water pools where there's lots of sediments, lots of oxygen deficit, and they turn out to be tolerant, short-lived organisms that are really not that great a food resource to the rest of the wildlife that turn out to come to streams as a place where they can feed. So streams are really an important place for a lot of wildlife. So here's the algae and the leaves that are being fed upon by the aquatic invertebrates. They in turn are fed upon by fish, by bats, and when they emerge from the water, because these are all immature stages, they all sprout wings and emerge from the water. So when they're in their aquatic stage, they're being fed upon by fish. But when they emerge from the water, they're fed upon by bats, birds, lizards in the riparian zone, spiders in the riparian zone. So those species that are really the nexus of terrestrial wildlife that comes to streams, not just to drink water, but to feed on these kinds of organisms. So the bottom line here is that droughts are causing and have been causing reductions in the diversity and abundance of the main forms of life that are supporting the wildlife that come to streams in the Sierra Nevada. So what to do about this? I think the first important thing is what I started off with, to understand how vulnerable habitats are changing now. the modeling of the future is just no substitute for direct observations of the present. So it's really important that more on-the-ground data gathering going on, and we not leave ourselves being dependent to the guesswork of computer modeling. Conserving riparian zones and groundwater recharge that cool and sustain flows are restoration measures that can be used to help preserve the connectivity of streams, the flows of streams, the cooler temperatures in streams. Restoration of meadows can do the same kind of thing. They serve as big sponges that can store and slowly release water to streams. And so there's a lot of restoration work that's been funded in the state of California in the last 5 or 10 years that hopefully will contribute to being able to establish these sorts of refuges. So those are the kinds of important restoration work that can be funded that are kind of band-aids. They're not the long-term answer, but they certainly can serve to sustain these things. And then the last thing is to uphold WOTUS. Anybody know what WOTUS is? This is the Waters of the U.S. rule. So this is what was established in the Obama administration that's now being challenged and may be removed under the Trump administration. But this is the rule that protects headwater streams and wetlands in the United States. Before WOTUS, after WOTUS, fully 2/3 of waters in the United States became protected that were unprotected before. So the vast majority of these habitats that are really the sustaining habitats to downstream navigable waters, which is what the Clean Act protected before, are now applied to these waters. So I think upholding and protecting WOTUS is an important letter to your congressman sort of thing. And that's all I have for you today.